Hello everyone and welcome to a new video. Yeah, I know it's been a while. It's been more than 1.5 years since I last posted my OS video, and I really expected that would do really good, but it did not do. And so I quit YouTube forever. But something really interesting happened recently, due to which I've come back from the dead to make my channel relevant again, which was never relevant to begin with. And that has to do with this tweet by Jonathan Blow. So, due to this tweet, that every time I read something to try and learn more about category theory, I come away unimpressed. It just always seems like vapid nonsense. So, due to this, it stirred up the beeness that is functional programmers who know category theory, and my timeline got flooded with these people who talk about category theory and functional programming. And they had some pretty nice arguments, which got me really interested in it. And then I saw this tweet by Dmitry Kovanikov, if I didn't butcher the name. So I partially agree and disagree. Category theory is quite abstract, and it's not obvious to how to make it practical for a newcomer. However, when you do make it practical, it's the best way to program. So that's quite the statement, best way to program. And then I went ahead and read his pragmatic category theory blogs, with like 2 blogs at that point. Now it's 3, I think. But yeah, that was very convincing. So I was pretty convinced that, okay, it's probably a good idea to give this a try. And then he also talked about that he's working on a configuration language based on category theory, which sounded really interesting to me. And so I decided, okay, you know what? I am already pretty decent at programming using procedures, objects, not using inheritance because I don't use inheritance. Screw that. And a lot of things. So I just wanted to improve myself. So I figured, okay, let's dive into this. Let's dive into functional programming and correspondingly category theory. So if you don't know what is category theory, it's a very abstract field of mathematics that is very intertwined with functional programming. And so functional programmers talk about it a lot. But it is very abstract and people really find it hard to make use of it, as reflective from this tweet. And there's like pretty good arguments that Jonathan had against the people who were like shilling it. So yeah, it's a pretty interesting thread. I would suggest you to read, and this one as well. But anyways, so yeah, I went ahead, read it, and full disclosure, I'm no expert on it, right? I'm just a very beginner in it. And I will talk about what I have studied. But first of all, let's talk about what's the interesting stuff. And that is whether you should do category theory or not, as per my experience. So, as per my exploration, I'm 70% inclined to say that you should do it. If you're already a pretty decent programmer, like if you already understand how to compose things, how to create interfaces, how to write procedures, all those things, and like you are able to write pretty good programs. Like I would not say like you are writing work of art, Shakespeare reincarnate, but you're writing something that, people find useful. Personally, I think I am at that stage, and that's why at this stage it might be helpful. And yeah, so this video I'm going to try to convince you why it is helpful. And then we'll also talk about what are the ways you can learn it. I'll explain how I did it, and then I'll explain a few other ways that I know of. Okay, so let's get down to business. First of all, let me just clarify what imperative and functional programming paradigms are. So in imperative programming, you step by step explain to the computer what you want to do. For example, copy memory from this memory region to a variable and then add +5 to it and then store it back to some another region. And object-oriented programming, procedural programming, these are all parts of imperative programming only. Then you have functional programming. And the way functional programming works is you define functions, generally pure functions. We'll get to pure functions, but you define functions like f, g, and then you compose bigger programs using these functions. So let's say the final program is a composition of f and g. So first of all, you apply g to the input, and then you apply f to the input, and you have a bigger program. And this is sort of the philosophy, but the pure aspect really matters. Why? Because you can just as well create functions here and compose them like this. So purity matters, and let's talk about what that is. So what purity is, right? Functional programming languages try to be as close to mathematical definition of functions as possible. And in math, functions, they are just, you give them an input and they return you an output. They don't have a computation. That means they never do infinite loop. That means all the functions, right? All the functions you define either in functional programming languages or in procedural languages, they always have that one possibility, right? They can go into infinite loop. And if we could figure that out beforehand, then we would have solved the Turing problem. So that's, I mean, the halting problem. So that's not a thing. That means for all the functions in all programming languages, I'm pretty sure, okay, but in all programming languages I know, none of them are pure mathematical functions. But so mathematicians have come with workarounds for this. We'll talk about it maybe later, but they still want to get as close to the mathematical definition. What's the another definition? So as you can see, they don't mutate anything. They don't have any side effects. If you give it an X, you expect a Y. You don't expect that the definition of log 2 will change, or like some supernova happens. You don't expect any side effects. So that's the definition of mathematical functions. There are more things, like it has to cover the entire domain and stuff, but let's just forget about it for now. As in, by domain I mean like all possible values of X. So functional programming languages try to have these pure functions. What are these pure functions? So these functions will take some input and they will return some output. Obviously they can go into infinite loop, but we'll put that case aside for now. And they try to have no mutations. So input value won't be changed. So you can assume nothing is passed by reference, and there won't be any side effects. So no supernova would happen, no logging would happen, no nothing. Okay, in a procedural code, these things can happen. Obviously a supernova can happen, and obviously logging can also happen. You can just do printf or Big Bang, whatever. So that's how they stay as close to the mathematical definition. And why is that relevant? Is because functional programming tries to be, it's not 100% true, but I'm mostly talking in terms of Haskell, because that's the functional programming language I know most about, and which is like one of the more truer to functional programming languages. So they try to have more mathematical semantics. So the semantics of a program in imperative programming languages are very hard to define in terms of math, with complete proper constructions. So that's what they try to avoid in functional programming. And one of the best ways to do that is obviously get rid of side effects, work with pure functions, because we already have pretty good models for functions and values, right? That would be set theory. You have sets, let's say, of some values, then a set of another values, and then you have functions that transform value from one set to another. So as you can see, this maps pretty well with the functional programming definition. And then they can, basically the idea is, once you denote everything in terms of mathematical constructs, then you can prove things in math and bring that to your programming. And vice versa is obviously also true, I guess. But that's essentially the idea. And another thing is, once you have these pure functions, they compose really well, because you know that, okay, only the output is what's relevant. So you can compose f after g after h after f dash after g dash, whatever. You can have this huge chain without any worries, because you know that only output of one is being fed to input. Output of one is being fed to input. There are no side effects. So reasoning about the program becomes very useful. Now, you may also say, oh, concurrency also becomes really good. And I'm not very convinced about that. I mean, even if you are programming in procedural languages, if you want to deal with concurrency, you want to have immutability. So, I mean, it's a use, but it's not the main thing. It's not the main thing about it, okay? So that's what functional programming does. It has constructs which are grounded in math, and then the knowledge from math, and we have centuries of research in math that can transfer here, right? Now, how well this happens, we can think about it, but yeah, that's what it is. So, which branch of mathematics does encode the semantics, right? Which branch of mathematics would encode the semantics for, let's say, a list of integers? Which branch of mathematics would denote the semantics for maybe of integer? And the answer is, so to some extent, you can actually use set theory, and set theory goes really well with functional programming, I think. For example, you must have heard of monoid in functional programming. Actually, you don't even need to know category theory for that. It's just a very basic set theory concept, which just from the set theory definition, you can make a lot of use. But anyways, so the field of mathematics that tries to encode this, now I believe multiple fields encode multiple parts. For example, I think lambda calculus also encodes a lot of things, but one that is really close to the functional programmer heart is category theory. And that is why it matters. Like, since this is essentially the mathematical foundation, now it may not have been derived that way because category theory is very abstract, but this denotes the foundational semantics for the functional programming languages, most of them, obviously, right? Or essentially in the context that functions are pure without side effects. In that case, it does that very well. And then if you know category theory, so if you know the foundational intuition and understanding of these constructs, the idea is, or is what I believe, and I'm starting to believe more and more, is that you can end up programming better programs because you know what are the foundational building blocks. And then once you know them, you are able to compose bigger programs in a more natural way. It's like you have a puzzle piece like this, and then you have another puzzle piece like let's say this, and then there is this puzzle piece which fits exactly here, right? And this is what category theory can help you find out faster with more and better intuition. You can't always figure this out yourself, right? Because you are not idiot. But this is what category theory does, and this is what math does in general. This is what theory does in general, right? It gives you more things in your toolbox to think about. And I will make this more concrete in just a second, but essentially that is the reason. So category theory is the foundational semantics for functional programming, and that is why it is useful. But I've not really gone into what category theory is, and I would not go into too much depth. Essentially what category theory is, so in a very funny way, what you do is you have a bunch of objects which you know nothing about, by the way. All you know is there are morphisms, so some arrows which denote something. We don't know exactly what they denote, so you just call them morphisms. Okay. And then what you do is, based on the properties of these morphisms, you figure out the properties of this category, properties of these objects, and just things in general. Okay. Yeah, it's exactly as abstract it sounds. In fact, in my opinion, category theory is not something you study from bottom up. It's something you study from top down. Because if someone were to tell you, right, that in the category of set, uh, set is, by the way, the category of all sets where each object is set. But when you study it in category theory, you don't know every object is set. So you only know the properties of these arrows, which are functions. And if I only tell you about the properties of these functions and what conclusions category theory makes out of that, it's very confusing and it's not intuitive, and it's nothing you can do out of that. You can not do any problem solving either, in my opinion. But that's about how that's like the biggest problem with it, that it is not intuitive at all, and that is because it generalizes a lot of things, and that is probably why it is applicable to type theory, right, which is our programming, to logic theory, which is true false, and then I also I think lambda calculus. This is called some isomorphism. So yeah, it is exactly as abstract as it sounds. So why is it useful? Now the thing is, what you want to do is you want to study especially this category called set or Hask. Hask is I'll explain what Hask is. It's not relevant, but set is the category where objects are sets, and a type is essentially a set, right? Integer type is set of all integers. Boolean type is set of two values, true and false, and so on. So in this category where objects are sets and morphisms are functions, so from a type A to type B, this would be, if this is A, this is B, this is F. If you study this category, right, then you learn a lot of good things. But if you study a lot of different categories, they don't really make sense. And I don't think there's much about them anyways. I'm probably wrong here. And because in category theory, what you do is you only analyze these morphisms. What you are really analyzing is their composition, because for it to be a category, there's like a few things that has to be there. There has to be an identity morphism, so from B to B, A to A, and also the composition of morphism F to G to H should exist. So it really only analyzes categories where morphisms compose, and these are functions, right? So what we end up finding out is patterns between composable functions. And why composable functions are very useful is because you compose functions to create bigger programs. And so it turns out to be pretty useful. And I'll give you one example, okay? So if you define in terms of category theory that, okay, your data, your type system has algebraic data types. What those types are, so all the primitive types, like let's say int, char, and all those things, bool, and then two operations. I think they are called bifunctors, but irrelevant. One is product and one is coproduct. Product is nothing but another type, let's say nt, with multiple types, let's say an int and a char. So it's like a struct. And then the other, so this is also called a product type, or simply a tuple of int and char. You must have seen this, right? So this is one thing that you call product in the category. And then there's another thing that is equivalent to tagged enums. I think typed enums or tagged union, whatever. So where this new type can either be an integer or be a character. So it's like a typed union, right? So with these two types of ways to compose types, one is product and one is coproduct, one is and, one is or, you can form any other type, okay, obviously, in this category. So now let me show you how category theory is useful, okay? So remember I talked about how would you denote the semantics of list, maybe using math. So these things, these containers essentially are what we call functors in the category theory. And now category theory for us proves that if you build any type using algebraic data types, so the primitives and then the and or, right? The product and co-product, you end up with another functor. That means, so they are functors, that means they have some properties, okay? We don't know what those properties are. I'll explain. We can talk about them later. But essentially what category theory can help us derive without even worries is that you can create any type. Let's call it a very complicated type, which is CT by accident. It is an integer, comma, bool, or it's a character, comma, list of characters. So you can create any complex type and this will also act as a functor. What that means is the properties that you derived for the functor that you were using for list, and maybe you end up using for that complicated type as well. And without category theory, you would actually probably have never seen this relationship that and actually, to not get into deep definitions, let's just say the big property of this functor is a map. So you can define mapping for functors. That means you can map on a list, obviously, right? You can map on a list to increase every element by 1, let's say. You can also map on any other complex type that you have created in a similar fashion that you have done for list, that you have done for maybe. And so yeah, that's actually one of the pretty useful insights that you can derive. Then there's also the fact that when you actually go into the deep math, right? Not even that deep actually, but once you start to formalize things, you also notice that dichotomy of types, that you only need the product type and the sum type to construct every other type. I'm only talking about algebraic data types. I'm not talking about something like dependent types, which are like even more hardcore type systems. I don't think Haskell does not have them. I don't think not. Like they don't. It don't have it. But in terms of these algebraic data types, you can. So you see this dichotomy, and personally, I had noticed it beforehand. Right, I knew that there's a struct and there's a tagged enum that is in Rust, let's say, or standard variant in C++, which happens to express almost everything. But I never actually formalized this personally, because obviously I'm not that smart. Maybe you have done it, but once you study math, you end up with more formalizations and you see, okay, these provide me with a lot of things. It's actually my argument that once you learn how to, like, what exactly are these things? From category theory, especially functors, applicative functors, monads, which are like very common with this meme. Monad is just a monoid in category of endofunctors. What's the problem? And I think there are a few other things. There's also monoid and semigroup, but those things are not really category theory dependent. You can learn them independently and make benefit of that. It's fine. But these things especially are pretty useful. So yeah. So that's my argument why you should learn category theory, because it denotes the exact semantics that the pure functional programming languages use, or the functional parts of programming languages use. And once you know these basics, you are able to see better ways to compose things. You will be able to see, okay, I can apply the functor mapping here. Here I can apply applicative functor mapping, and so on and so forth. But there's a caveat here, okay? Many people think, okay, category theory will help them model problems, which is completely wrong in my opinion. Remember I talked about how category theory is completely abstract. Most of the things, it's my hunch, but I don't think like I think most of the things are not derived in category theory. Instead, they're derived in their respective mathematical branch. Let's say a monoid, or let's Cartesian product. Those things, they're defined in this respective mathematical field, and then they're mapped to category theory. How do they map there? Because it's sort of a generalization over a bunch of fields, right? Rarely you find something in category theory that is like unique, that's completely derived from it. I'm pretty sure there are things. I think even monad is something that's completely derived from it, but generally they are not. And that's why I believe like it's pretty hard to model problems in terms of category theory and then solve them. And I'll give you an example in a moment. Actually, let's start with the example. So this is a blog on version controls using category theory. So turns out you can model VCS in terms of category theory. And this article had some very huge claims that you'll never have merge conflict. Guaranteed to never ever have a merge conflict. And so I was very intrigued that, oh wow, can we model using category theory and never ever have a merge conflict? And then it turns out you will still have merge conflicts, obviously. You'll just keep them differently on the disk, or like however you want to persist it, and at the end you'll essentially have to do something like merge. And I think that looks like a merge conflict. Even the author agrees, but the author goes on to say that, okay, no, it's different. But I read this, and in my opinion, what he's suggesting here is like he's saying that, okay, flattening would be a completely different commit, and it can be natural defined or whatever, but it's still merge conflict resolution that you'll have to do. And that's what my point is actually, that no, if this is a problem statement to never ever have a merge conflict, you are not going to solve it by category theory, most probably. If it was solvable, it would have already been solved, because we are not stupid people, right? I am, but like most of the people who solve problems are not. So they would have already solved it. Just because it's modeled differently, probably that won't stop them. So you don't want to try to model problems using category theory, in my opinion, to solve them. What you want to do is, whenever you have a problem, you still have to think about it in the context. Come up with small composable units, or just small units, and then you will see, especially if you're working with algebraic data types and pure functions, that using these category theory constructs, functors, applicatives, monads, you can compose them in very unique ways that you would have never thought. And this comes from the property of purity and no side effects and algebraic data types. And you may argue that, okay, why do you need to learn these things from category theory for that? Can't you just learn functional programming? And that is true, you can, but you won't have as good of an understanding and intuition about them. Because even in Haskell, like if you go and look, okay, what's the definition of functor in Haskell? You will see, okay, it has to have a function that goes from a to b, to a function that goes from f of a to f of b. F is the functor. And this is the signature, but there are other properties that it has to satisfy, which many times books don't even mention. And those are actually that the functions that you get after applying functor on a function have to be composable. And those things really make a lot more sense when you learn them from category theory, or at least know the category theory derivation. So yeah, that is my argument why you should learn category theory. All right. Okay. So if you're still here, I believe you are sort of convinced that you should try category theory. So here are the resources. I would suggest going through this book, by Bartosz Milewski. I hope I did not butcher the name. I'm sorry. He's a great guy, great book, although a bit hard to follow and lacks a bit of depth. So, I mean, depth in the sense of explanation, not the concepts, for which I would so rather suggest his lecture series on this, which is in a lot more depth. If you are like a pretty stupid person like me, these will help you follow category theory. These are pretty hard to follow. Like I gave up after products and co-products chapter. So this is pretty good. Then pick up a functional programming language. By the way, here I would suggest only the first playlist. There are two more playlists, category theory 2 and 3. The first one is good enough to get started with. Then you should consider writing Haskell or some other language that has first class support for category theories, things like functors. So let's say you were thinking of Scala, which I don't know why would you think, but you can just say Scala functors. They exist. You can try. You can try OCaml, I believe. Or you can try Haskell. I would suggest Haskell actually. It's a great language. And for Haskell, there's haskell.org/documentation, which has a lot of books. Personally, I read this one, and then I also wrote a program. And actually, only after going through this entire 20 playlists, all right, a bunch of conference talks, which I'll link in description, this book, and then writing my own project, which was a basic Git-like VCS implementation, which has support for commit, checkout, log, basic things you would expect. Only after this, I was able to figure out that, okay, yeah, category theory was useful. Like Steve Jobs said, you cannot connect the dots going forward. You can only connect them looking back. That really makes sense. So yeah, I would suggest the foundational things for category theory. You can choose some other book if you like, or other lecture series. Whichever functional programming language you are going to do, right? Some books on that, and then some projects by yourself. And I think that would be a pretty good start. Join communities and code.